There is an important note. We've tried to focus on the idea, the concept of the integral, but it's important to remember its roots. So when we talk about this integral from some starting point to some ending point of some function with respect to x, what that translates to is a sum of the function value at various points times elements of width. What we've seen up to now when we talked about areas was positive function values. But there's no reason why the function itself can't be negative. No reason at all. So we just have to do a quick mapping between what our understanding of area is versus what the integral is. So they're related but not perfectly identical because of this possibility of negative function values. So let's take a look at this function here. So it curves up and down. It has parts where the function is below 0 and values where the function is above 0, then below 0, then above 0 again. Our question is going to be, how do we relate that back to area, or how do we relate the integral and the area calculations? Well, imagine if we took this and divided it into small subintervals, which is exactly what the integral means. When we do that, on the regions that are above the axis here, f of x is going to be positive, and so it's going to add to the total in the sum. Whereas when we take a look at the points that are below the axis in regions B and D here, on those regions the f of x values are negative, and they are going to subtract. They're going to have a net negative effect on the total of the sum. And that's just how we do things. We add positive numbers and negative numbers. The negative numbers subtract away and they cancel something out. So at the end of the day, the elements that are going to have positive contributions to the total are A, C, and E, and the ones that have negative values are those that are below the axis. In all cases, the delta x is always positive. We're always moving from left to right, and so that doesn't change. The only thing that changes in our area calculations are the heights. What that means is the idea of area gets a little sketchy. So the integral from a to b, so the starting point to the end point of this function, in terms of the positive areas. So b, if I actually talked about that area, it would be 3 square units. So it would be positive. But the integral over this interval from a to b, I apologize for the integral similarity. This integral over the interval from a to b would be made up of the area in a, and then we would subtract the area that is in b. If b is a positive area, so area is always positive, then the integral might not be positive, but it'll be related to the area. Then whatever the area is in c, it's made up of function values that are positive, so it would add to the total, and then whatever the area is in d, it's represented by negative function values, so we'd subtract that from the total. And finally, we would add e on the end. Now, depending on your experience so far, you might think, why are we doing negative things? What sense does that make? Well, if again, we think of this back at our original motivating example of velocity against time and us trying to find the change in position, this makes complete sense. If we have positive velocities, think of that as forward. And then on the negative side, we might have backwards motion. In that scenario, well, we go forward for a bit, and then we go into reverse, and we go backwards for a bit. How much have we changed in position? Well, whatever our forward motion was, minus the amount that we move backwards. Then plus the amount we move forwards, then backwards, then forwards. We expect things to cancel out. In fact, if they didn't, we would be worried. So don't think this is some esoteric thing. This is exactly what we want in most physical applications, is to be able to cancel out when appropriate motion or totals in different directions. It's completely reasonable, and we shouldn't be shocked by it. The challenge is when we try to map things back to areas, we have to be just a bit careful about that and that analogy. So a quick closing here. Riemann sums are, again, any sum that has this structure of a height times a width. Anytime we see that, we know that we're in a regime where there's probably a way to tie this to an integral. And what we usually do in applications is start with this idea of adding things up times little units of x or time, and then turning it into an integral. What we can also do then is use them as an approximate value by using a fixed number of intervals. Instead of saying, oh, I want the perfect ideal limit with an infinite number, we can always approximate with a finite number. What we're going to see is that there are easier ways to get the exact value in many cases by using the reverse of derivatives, which shouldn't come as a huge shock because we're going from velocity back to positions as our motivating example. But we'll see how we can officially turn what we've been working with here into the classic calculus integral next week.